Hello friends, welcome back. In the previous sessions, we have studied graph isomorphism, paths, cycles and circuits. Also, we gave a characterization for bipartite graphs. In this session, we will discuss an important types of circuit known as Eulerian circuit is one which passes through every edge of a pseudograph and Hamiltonian graphs. Recall that a trial in a graph G is a walk in G in which the edges are distinct. That is, no edges of G appears in the trial more than once. A trial in G is called an Eulerian trial if it includes every edge of G. An Eulerian circuit in a pseudograph is a circuit which contains every vertex and every edge. An Eulerian pseudograph is a pseudograph which contains an Eulerian circuit. For example, consider the graph. In this graph, the circuit A, B, C, E, F, C, D, A is not Eulerian because it does not contain the edge BD. Later we will show that this graph possesses no Eulerian circuit, so it is not an Eulerian graph. The next example will illustrate the difference between a circuit and an Eulerian circuit. See the graph. The circuit A, B, C, D, E, F, G, H, F, A is not Eulerian since while it includes all vertices but it omits 4 edges. The graph is Eulerian, however, A, B, C, D, E, F, G, H, F, A, D, B, E, A is an Eulerian circuit. Now we present a simple test for the presence of an Eulerian circuit in a pseudograph. First, since an Eulerian circuit provides a walk between every pair of vertices, an Eulerian pseudograph must be connected. That is, a pseudograph is connected if and only if there exists a walk between any two vertices. Since every UV walk contains a UV path, then if a graph is connected, then there is actually a path between any two vertices, not just a walk. Next, we will give a simple but useful characterization of Euler graphs and graphs with Eulerian trials. First one is, a connected graph G is Eulerian if and only if the degree of every vertex is even. To prove this, we need the following result. Let G be a graph in which the degree of every vertex is at least 2. Then G contains a cycle. Proof. If G is a pseudograph, then it contains a cycle since any loop is a cycle of length 1 while a pair of parallel edges gives a cycle of length 2. We now suppose that G is simple. Let V0 be any vertex of G. Since degree of V0 greater than or equal to 2, we can choose an edge E1 with one end V0 and the other V1. Say, since D of V1 greater than or equal to 2, we can choose an edge E2 with one end V1 and the other V2, say. Different from V0. If we repeat this process, since G has only finitely many vertices, we must eventually choose a vertex which has been chosen before. If Vk is the first such vertex, then the walk between the first two occurrences of Vk is a cycle. Proof of the main theorem. A connected graph G is Eulerian if and only if the degree of every vertex is even. Proof. Suppose that G is Eulerian. Let C be an Eulerian circuit in G, starting and ending at the vertex U. Since if V is a vertex of G different from U, V must be a vertex on the circuit C, since U is connected to V, G being connected, and C involves every edge of G. Moreover, each time V is met on the circuit C, it is entered and left by different edges because each edge of G only occurs once in C. Thus, each occurrence of V in C represents a contribution of 2 to its degree. This degree of V is even. Finally, since C begins and ends with U, the first and last edges of C contribute 2 to the degree of U and any internal occurrence of U on C will also contribute 2 to degree of U. Hence, degree of U is also even. Thus, the degree of every vertex of G is even as required. Conversely, suppose that G is connected and that every vertex is even. We use induction on the number of edges of G to show that G is Eulerian. Firstly, if there are no edges, then since G is connected, G must be consist of a single vertex U with a degree 0. Then the trivial circuit C equal to U involves all the edges of G, since there are none. Thus, G in this case is Eulerian. Now, suppose that G does have edges. Then, since G is connected, no vertex of G can have degree 0. Thus, since each vertex is even, each vertex must have degree at least 2. Then, by the previous result, G contain a cycle C say. If C contain every edge of G, then we are finished, since then C is an Eulerian circuit. If C does not contain every edge of G, then we delete from G every edges in C to form a new possibly disconnected graph H, which has fewer edges than G, but the same vertex set. Also, the vertices of H are still even. Now, assuming the induction hypothesis that the result holds for all graphs with less edges than G, each component of H must be Eulerian because the degree of each vertex of H is even. Moreover, since the components were formed by the deletion of the edges of C, each component has at least one vertex in common with the C. We now obtain an Eulerian circuit for G as follows. Start at any vertex of C and go around the edges of C until a vertex belonging to a non-empty component of H is met. Say this vertex is V1. Then go to an Eulerian circuit in this component. Starting and ending at Vt, once back at Vt, resume going round C until the next non-empty component of H is met and repeat the process of going on an Eulerian circuit in this new component. We repeat this procedure, eventually going all the way around C back to our starting point, making an Eulerian circuit in each non-empty component of H on the way. Then, since the edges of G are just those of H together with those of C, we have completed an Eulerian circuit of G. Next is characterization of graphs which have Eulerian trials. Theorem. A connected graph G has an Eulerian trial if and only if it has at most 2 odd vertices, that is, it has either no vertices of odd degree or exactly 2 vertices of odd degree. Suppose G has an Eulerian trial. Then if V is a vertex different from the origin and terminus of the trial, the degree of V is even. Thus, the only possible odd vertices are the origin and the terminus of the trial. And if these coincide, then in fact we have an Eulerian circuit and every vertex is even. Conversely, suppose that G is connected with at most 2 odd vertices. If G has no odd vertices, then G is Eulerian and so has an Eulerian trial. This leaves us to treat the case where G has 2 odd vertices, U and V say. G cannot have just one odd vertex, since in any graph odd vertices occur in even times. Now, let G plus E denote the graph obtained from G by adding a new edge joining U to V. Then E increases the degree of U and V by 1, and so in G plus E every vertex is even. Hence, G plus E has an Eulerian circuit, say C equal to V0, E1, V1, E2, etc. En, Vn, involving each edge of G plus E exactly once. We may suppose that E1 equal to E, V0 equal to U, V1 equal to V, and so Vn equal to U. Then deleting the edge E from the circuit gives the Eulerian trial V1, E2, etc. Vn, En from V to U in G, since it involves each edge of G exactly once. For example, see the figures. Here we can draw the first and second diagram without lifting one's pencil from the paper and without repeating any lines, but the third cannot. With our present terminology, the Königsberg bridge problem asks if the pseudograph is Eulerian. That is, we have to chosen a vertex in the pseudograph of the Königsberg bridge problem and find a arc which involves all the edges exactly once and leads back to the chosen vertex. A graphical representation of the Königsberg bridge problem is given below. Here the degrees of each vertex is odd, so this graph does not contain an Eulerian circuit. The next graph has an Eulerian trial. Here vertices A and B have degree 3, J and K have degree 2 and all the others have degree 4. Since the graph is connected and A and B are its only odd vertices, there exists an Eulerian trial from A to B. One Eulerian trial is A, G, H, F, D, G, J, H, I, F, E, L, K, L, B, C, A, D, C, E, B. Consider the graphs G1 and G2. Here the graph G1 has an Eulerian trial, but the graph G2 is an Eulerian graph. Now we will move on to Hamiltonian graphs. Here we will discuss circuits which contain each vertex of a graph exactly once. A Hamiltonian cycle in a graph is a cycle which contains every vertex of the graph. A graph G is called Hamiltonian if it has a Hamiltonian cycle. Note that some authors define a Hamiltonian circuit as a circuit in which every vertex except the first and last appears exactly once. A circuit with no repeated vertices except the first and last is a cycle, so a Hamiltonian circuit is a cycle. Thus the terms Hamiltonian circuit and Hamiltonian cycles are synonymous. Consider the two graphs. Here G1 is Hamiltonian since the cycle A, B, C, D, E, A is a Hamiltonian cycle, but G2 is not Hamiltonian. We can prove G2 is not Hamiltonian. Suppose that G2 has a cycle H which contains every vertex, then H will contain A which is a vertex of degree 2. Since we cannot enter and leave A on the same edge, since edges of a cycle are distinct, it follows that both edges incident with A have to be part of H. In particular, CA is in H. The same argument applied to B shows that CB is a part of H and similarly CD and CE are in H. So, all four edges incident with C are part of H. This situation is impossible since H is a cycle. The vertex C can appear only once unless the cycle begins and ends at C. Note that there are no non-trivial conditions that would be necessary and sufficient for the existence of a Hamiltonian cycle. By deleting the last edges of a Hamiltonian cycle, we get a Hamiltonian path. However, a non-Hamiltonian graph may possess a Hamiltonian path. That is, Hamiltonian paths cannot always be used to form Hamiltonian circles. Consider the example. Here G1 has no Hamiltonian path and so no Hamiltonian cycle. G2 has a Hamiltonian path BACD but has no Hamiltonian cycle, while G3 has the Hamiltonian cycle ABDCA. Some more examples for Hamiltonian graphs are given in the figure. Around the world problem. Hamiltonian graphs were named after Sir William Hamilton, an Irish mathematician who invented a puzzle called the equation game. The puzzle invented a dodecahedron in which each of the 20 vertices was labeled by the name of some capital city in the world. The object of the game was to construct, using the edges of the dodecahedron, a tour of all the cities which visited each city exactly once, beginning and ending the same city. In other words, one had essentially to form a Hamiltonian cycle in the graph corresponding to the dodecahedron. This figure shows a Hamiltonian cycle in the corresponding graph of the dodecahedron. Some important notes. First one, the n cycle with n distinct vertices and n edges is Hamiltonian. Second one, given any Hamiltonian graph G, then if G dash is a supergraph of G obtained by adding in new edges between vertices of G, G dash will also be Hamiltonian, since any Hamiltonian cycle in G will also be Hamiltonian cycle in G dash. In particular, since Kn, the complete graph on n vertices, is such a supergraph of an n cycle, so Kn Hamiltonian. Third one, a graph G will be Hamiltonian if and only if its underlying simple graph Hamiltonian, since if G is Hamiltonian, then any Hamiltonian cycle in G will remain a Hamiltonian cycle in the underlying simple graph of G, provided we delete the appropriate parallel edges. Conversely, if the underlying simple graph of G is Hamiltonian, then G will also be. Fourth one, given a simple graph G with n vertices, since G is a supergraph of the complete graph Kn, we can construct step by step simple supergraphs of G to eventually get Kn simply by adding an extra edge at each step by 2 vertices that are not already adjacent. We illustrate this by the figure. Fifth one, if we start with a graph G that is not Hamiltonian, then since the final outcome of the procedure is the Hamiltonian graph Kn, at some stage during the procedure we change from a non-Hamiltonian graph to Hamiltonian graph. For example, the non-Hamiltonian graph G1 above is followed by the Hamiltonian graph G2. Notice that since supergraphs of Hamiltonian graphs are Hamiltonian, once a Hamiltonian supergraph is reached in the procedure, all the subsequent supergraphs are Hamiltonian. Definition: a simple graph G is called maximal non-Hamiltonian if it is not Hamiltonian, but the addition to any edge connecting two non-adjacent vertices form a Hamiltonian graph. For example, the graph G1 is maximal non-Hamiltonian since the addition of the edge AB gives the Hamiltonian G2 as shown, while the other possibly the addition. Suppose H is a cycle in a graph G. First one, for each vertex V of H, precisely two edges incident with V are in H. Hence, if H is a Hamiltonian cycle of G and a vertex V in G has degree 2, then both edges incident with V must be a part of H. Second one, the only cycle contained in H is H itself. We say that H contains no proper cycles. We show that the Peterson graph is not Hamiltonian. Suppose H is a Hamiltonian cycle, then H must contain at least one of the 5 edges connecting the outer to the inner vertices. Since the graph is symmetric, there is no loss of generality in assume that AF is part of H. Here precisely one of the two edges FH and FI is in H. Again by symmetry, we may assume FH is a part of the cycle while FI is not. Since Fi is not in H, but two edges incident with I must be in H, then Ig and Id are in H. Now precisely one of the edges GB, Gj is in H. Suppose first that GB is in and Gj is out. Because precisely two edges incident with J are in H and Gj is not, both Gh and Ge are part of H. Thus, CH is out and both BC and CD are in H. Then we get H contain a proper cycle B, C, D, I, G, B, a contradiction. We conclude that GB cannot be part of H and hence that Gj is, by a similar argument we can show that H contain a proper cycle. Again a contradiction. So the Peterson graph is not Hamiltonian. Dirac theorem. If G is a simple graph with n vertices where n greater than or equal to 3 and the degree of V greater than or equal to n upon 2 for every vertex V of G, then G is Hamiltonian. Proof. We suppose that the result is false. Then for some value n greater than or equal to 3, there is a non-Hamiltonian graph G in which every vertex has degree at least n upon 2. Using this G, we obtain a contradiction. G cannot be complete since is Hamiltonian. Thus, there are two non-adjacent vertices U and V in G. Let G plus UV denote a supergraph of G obtained by introducing an edge from U to V. Then since G is maximal non-Hamiltonian, G plus UV must be Hamiltonian. Also, if C is a Hamiltonian cycle of G plus UV, then it must contain an edge UV, since otherwise it would be Hamiltonian cycle in G. Thus, choosing such a C, we may write C equal to V1, V2, etc. Vn, V1, where V1 equal to U, Vn equal to V, and the edge Vn, V1 is just UV, that is UV. Now, let S equal to set of all Vi belongs to C such that there is an edge from U to Vi plus 1 in G, and T equal to set of all Vi belongs to C such that there is an edge from V to Vi in G. Then Vn belongs to T, since otherwise there would be an edge from V to Vn equal to V, that is a loop, impossible because G is simple. Also, Vn does not belongs to S, interpreting Vn plus 1 as V1, since otherwise we would again get a loop, this time from U to V1 equal to U. Thus, Vn does not belongs to S union T. Then we get number of elements of S union T less than in equation number 1. Also, for every edge incident with the U, there corresponds precisely one vertex Vi in S. Thus, number of elements in S equal to degree of U, equation number 2. Similarly, number of elements in T equal to degree of V, equation 3. Moreover, if Vk is a vertex belong to both S and T, then there is an edge E joining U to Vk plus 1 and an edge F joining V to Vk. This would give C dash equal to V1, Vk plus 1, Vk plus 2, etc. Vn, Vk, Vk minus 1, etc. V2, V1 as a Hamiltonian cycle in G, a contradiction since G is non-Hamiltonian. This shows that there is no vertex Vk in S intersection T, that is S intersection T is phi. Thus, number of elements of S union T equal to number of elements on S plus number of elements on T. Hence, by equation 1, 2 and 3 above, degree of U plus degree of V equal to number of elements on S plus number of elements on T, which is equal to number of elements on S union T strictly less than N, equation number 4. This is impossible since in G, degree of U greater than or equal to N upon 2 and degree of V greater than or equal to N upon 2. And so, degree of U plus degree of V greater than or equal to N. The contradiction tells us that we have wrongly assumed that the result is false. Theorem. Let G be a simple graph with n vertices and let U and V non-adjacent vertices in G such that degree of U plus degree of V greater than or equal to n. Let G plus UV denote the supergraph of G obtaining by joining U and V by an edge. Then G is Hamiltonian if and only if G plus UV is Hamiltonian. Proof. Suppose that G is Hamiltonian. Then, as noted earlier, the supergraph G plus UV must also be Hamiltonian. Conversely, suppose that G plus UV is Hamiltonian. Then, if G is not Hamiltonian, we obtain the inequality degree of U plus degree of V strictly less than n. However, by hypothesis, degree of U plus degree of V greater than or equal to n, hence G must be Hamiltonian also as required. Let us summarize this session. In this session, we have discussed Euler circuits and Euler trials in pseudographs. We gave characterization for them, also Hamiltonian graphs, and show the Peterson graph is not Hamiltonian. We also discussed about Dirac theorem. Hope you all enjoy the session. See you next time. Until then, bye.